So first of all, you will hear me say these words over and over again. So I want to give you a formal definition. So whenever I say with high probability, something happens. So whenever I say with high probability, some event epsilon happens. What I mean by this is that if you take the probability of epsilon over an instance of our problem of size n, and if you take the limit of this probability when the size tends to infinity, then this limit is 1. Okay. And whenever I say with low probability, basically I mean that this limit is 0. So for any given size, you might have different probabilities, but as the size tends to infinity, I want the probability to tend to 1. Okay, that's the first thing. The second thing that we will use a lot is the definition of expected value. I expect you to know this, but I'm going to define it anyway. Since we're using discrete random variables, if I have a random variable x, the expected value of x is the sum over all values that this big X can get. And this is just the probability that the value of big X is small x times small x. Okay? So basically, this is the average value of x. And we sometimes, instead of writing the expected value of x, I will just write mu. So whenever I write mu, I mean the expected value of some variable, usually that's x. Okay, so today we're going to analyze a relatively simple process, but we will get some nice results about it. And the process is a balls and beans process. So suppose that I have n different bins. So this is bin number 1, bin number 2, so on, and this is bin number n. And let's say that I also have m balls. And let's say that my balls are all identical. I don't care which ball is which, but the bins are different. And what I do is that I just take the balls, and for each ball, I randomly throw it into one of these bins. And I do this with equal probability. So each ball goes into bin number 1 with probability 1 divided by n, into bin number 2 with the same probability, and so on. This is the process that we want to analyze. Now, what is the expected number of balls that I will have in each one of my bins? If I just throw n balls into n bins. Well, of course, we expect that on average, each bin should get m over n balls, right? But can we really prove that formally? So let's say that I take, okay, let me give it a name. Let's say I say bk is the number of balls in bin number k. Okay. And let's say that I define some random variable xij, and I say that xij is 1 if the ice ball is thrown into bin j. And it's 0 otherwise. Okay? So then I can basically say that the number of balls in bin k is basically the sum of some of these indicator variables. So it's the sum of xik's, where I goes from 1 to n, right? And now here I can use linearity of expectation. I can say that if I want to find the expected number of balls in bin k, then this is just the sum of the expected values of these xik's. Okay. And we have linearity of expectation even if these variables, are interdependent. So they don't have to be independent for linearity of expectation to hold. Okay, now what is the expected value of a single xik? It's that it's basically the probability that I put ball I into bin k. But I said I choose uniformly at random, so this probability is just 1 over n. Right? And so this whole sum is m over n. Okay, so this was kind of a trivial result. Yeah, if I'm throwing m balls randomly into n bins, I expect that on average, I get m over n balls in each bin. Now, my question is, how far can I get from this average? So let's talk about events that are likely here and events that are not likely. It's very likely that my balls are really going to be spread around. So if I ask, for example, what is the probability that all of the balls end up in bin number 1? That probability is going to be really small, right? Basically, it would be 1 over n to the power of n, right? So I can say that with high probability, not all the balls will be in bin number 1. Okay. But can I somehow say that with high probability, none of my bins will have more than some number of balls? Can I say that with high probability, no bin gets, let's say, more than n balls? Okay. So let's actually simplify this a little bit, and let's say that the number of balls and bins are the same, because as usual, I don't like to work with too many variables. So let's say I'm putting n balls into n bins. And so on average, I expect that each bin gets 1 ball. Now, how likely is it that I have a bin that has, for example, 10 balls? Can I say that with high probability, no bin will have 10 balls? Actually, intuitively, no, right? Because as the number of balls and bins increases, intuitively, we think that it would be more probable that at some point we will have a bin that has more than 10 balls. So if I want to say that the probability, so here's what I want to say. I want to say the probability that a single bin contains, let's say, more than k or at least k balls. I want to say this probability is really small, and I want to say that it tends to 0 as n grows. But I have to choose the right value for this k. And again, intuitively, if I just choose a constant for k, this wouldn't work. Right? And to see that, just think about what happens if we say, what is the probability that there is some, okay, let's just do this. Let's say that I set k to 2. So if I set k to 2, I'm basically asking, what is the probability that there is a bin that contains at least 2 balls? Okay. But what is that probability? So if the number of balls and the number of bins is the same, the only case where I don't have a bin that contain at least 2 balls is if all the balls go into distinct bins. Okay. So what is the probability that all the balls go into distinct bins? Well, that's just going to be n factorial divided by n to the power of n, right? Because all of our possibilities are n to the power of n. And if I want all of my balls to go into different bins, for the first ball, I have n choices. For the second ball, I have n-1 choices, and so on. And so the probability that I have at least one bin that has more than one ball is 1 minus this. And as you see, this is a large number because this tends to 0 as n gets large. So you can do similar analysis. Of course, it gets a little bit more complicated as you increase the k, but you will see that no constant k would really work. So let's look at the opposite end of the spectrum. What happens if I set k to be n? As we saw, that's very unlikely that we have one bin that has all the n balls. But what if I set k to be half of n? That's also going to be quite unlikely, right? So we don't know what the nice value for k is. So let's just keep it a variable, and let's just find some bounds on the probability that I have at least a bin that contains at least k balls. And then after we find a bound on the probability based on n and k, we can come back and then we can choose the right value for k based on n. Okay? So let me do the same thing that I was doing last time and try to break this probability that we were interested in into several smaller events and smaller probabilities. Okay. So I'm going to define an event, epsilon jk, and I'm going to say that this is the event that says bin number j has at least k balls. Okay, and I'm going to define its start version, so E star of jk, to be the event that bin j has exactly k balls. Okay, if I can find this probability, then of course I can find this probability because I can just sum these to get that one. So what is this probability? What is the probability that bin j gets exactly k balls? So I have n balls and I'm throwing them into n bins, right? So actually, I don't want to reuse k, so let's just call this one I, and let's say that bin j has exactly I balls. Okay. So I have to choose which one of my I balls are going to go into bin j. So I first choose the I balls from the n balls that I have. And then those I balls have to go into bin j. So the probability that each one of them goes into bin j is 1 over n. So that's 1 over n to the power of I. And all the other balls have to go to the other bins. So that would be n minus 1, or actually let me write it as 1 minus 1 over n to the power of n minus I. Okay. This is the exact probability, but it's not such a nice thing to work with. So can we maybe simplify it a little bit? Well, I imagine that as n grows, this thing gets closer and closer to 1. So this part will probably not have much of an effect. So I can maybe approximate and get rid of it. Maybe I can say that this is at most n choose I times 1 over n to the power of I. So I'm just saying that this part is definitely less than 1. So I just get rid of it. Okay, and now I can just use the approximation for n choose I. And I can say that n choose I is at most NE divided by I to the power of I, right? And I had a 1 over n to the power of I. Okay. So if I multiply these two things, the n's cancel, and this would just be E over I to the power of I. Okay. So now I have a simpler bound. Now the probability is not exact, but I at least know that the probability that a particular bin J has exactly I balls is at most E divided by I to the power of I. Okay, so now how do I find a bound for this one? I can just use that. So let me erase this side. Now, okay, and this thing that I computed here was the probability of this event. Okay. Now, what is the probability of this event? That bin J has at least k elements. Well, it's just the sum of these probabilities, right? Because if it has at least k balls in it, it either has k balls or k plus 1 balls or k plus 2 balls and so on. So it's just the sum for I from k to infinity, but okay, can have at most n balls. So k to n and E divided by I to the power of I. Okay, let's find this sum. Okay, this is like a geometric series, right? So I can say that this sum is at most the same sum if I just go to infinity instead of going to n, right? And basically you can write it like this. It's E over k to the power of k times 1 plus at most this plus E over k plus E over k squared. So, okay, because all of those i's are more than k. And so this is at most, just solve the geometric series. It's E to the power of k to the power, E over k to the power of k over 1 times 1 over 1 minus E over k. Okay, now I have a nice bound. I don't know if you consider this nice, but at least I know that the probability that a particular bin J has at least k balls is bounded by this expression. So now, based on this, what do you suggest I put for k? So I want to say that with high probability, I don't have any bin that has so many balls, that has k balls or more. And I have this bound on the probability that one of my bins, that bin J, has k balls or more. So what would you choose for k here so that you get a nice bound based on n? Yes, that's actually true, yeah. So if you just choose k to be log of n, you will probably get a good bound here. Now, because I want to get a really nice bound, I'm going to set k to be a very specific value. If I set k to be e times the natural log of n divided by natural log of n, this thing. But this just came out of the algebra. You can just think that I'm setting the k to be some constant times log of n, right? But anyway, if you set k to be this, then this probability would be at most 1 over n squared. Okay, but again, it's up to you. You can change the constants, you can play with this and get other bounds there as well. So I have a k that is basically logarithmic in n, like a little bit less than logarithmic because we have divided by log log. And for every single bin, I know that the probability that this bin has at least k balls is at most 1 over n squared. So this probability is going to tend to 0. So this probability is very low. But that's not exactly what I wanted, right? So what I wanted was the probability that there exists a bin that has k balls or more. Okay? So what I want is the probability of the union of these events. Where j goes from 1 to n. Okay, so the probability that either bin number 1 has more than k balls, or at least k balls, or bin number 2 has at least k balls, or so on. But I can just use the union bound here. And what is the union bound? It's just says that the probability of a union of a bunch of events is at most the sum of the probabilities of those events. So I can just say that this is at most the sum for j from 1 to n of the probability of this event that I had, which is basically that bin j has at least k balls in it. But this probability was at most 1 over n squared, and I have n of it, so this sum is at most 1 over n. And actually, this is why I had this particular choice of k, because I wanted to get 1 over n squared here, so that when I apply the union bound, I still get a probability that tends to 0. Okay. So now I can say that with high probability, there is no bin that contains k balls or more. Okay. Now, again, in this session, we're not really seeing algorithms, but we will later on talk about these things in terms of algorithms. So I would, for example, say that with high probability, the runtime of this algorithm is at most this much. Okay. Nice. Let's see if you've probably seen this next example already, but okay. Let's actually go into this with more detail. So let's say that the number of bins and balls are not the same again. So let me erase this one. So we saw that if the number of bins and balls is the same, then of course with high probability there is going to be a ball that contains at least a bin that contains at least 2 balls. But now I want to see what happens if the number of balls and bins are not the same. So again, let's say that I have m balls, but I have n bins. And I want to know what is the probability that there is a bin that contains at least 2 elements. Okay, so this is what you will see in probability courses as the birthday paradox. It's this idea that if you have, let's say, a class of people and these people are born on random days of the year, how many people do you need to be in that class so that you can say with some confidence that there are 2 people who have the same birthday? So just think of people as balls and days of the year as bins. But going to stick to balls and bins. So I'm throwing m balls into n bins, and I want to know how big should I choose the number of balls. So how many balls do I need before I can say that with high probability, there are 2 balls that go into the same bin. Again, the example that we saw at the beginning of this session was that if the number of balls is equal to the number of bins, then we can say that with high probability we have that, right? But how small can I make the number of balls? For example, of course, if I have just 1 ball, it's impossible to have more than 1 ball in a bin. If I only have 2 balls, again, it's very unlikely that the 2 balls get into the same bin. And generally, if I have k balls, I can again say that the probability is not going to grow as n tends to infinity, and it's actually going to tend to 0. So the number of balls, again, cannot be a constant. It has to somehow depend on the number of bins. So m has to depend on n. But again, we want to figure out what kind of dependence is enough for us. So let's try this. Okay. So let's just define our variables. And this is what I want to define. I want to say that I define an event epsilon I, and I define it as the event that the ice ball falls into an empty bin. So into a bin that was empty before we threw this ball. Okay? So what do I want? I want the probability that no 2 balls are in the same bin. So the probability that every ball has fallen into an empty bin. So I want the probability of the intersection of all the events that I had for my balls, all epsilon I from 1 to n. Okay, but this is just the probability of the first event times the probability of the second event, assuming the first event, times the probability of the third event, assuming the first 2 events, and so on. Okay. So now what I'm interested in is one of these terms. So what is the probability that the ice ball falls into an empty bin, assuming that all the previous balls have already fallen into empty bins at the time that they were thrown? So what is the probability that when I throw the ice bin, the ice ball, it goes into an empty bin, assuming that all the previous ones were already in distinct bins? Okay. So what is this probability? So I had I-1 balls before, and they basically occupy I-1 different bins. And I have n bins overall. So I have to choose one of the n-I+1 free bins from the n bins, right? I basically get this probability. Or I can also write this like as 1 minus I-1 divided by, because I-1 of the n bins are already occupied. Okay, so this probability, the one that I'm actually interested in, is going to, okay, I'm just going to write it here again. So I'm interested in the probability that everything goes into distinct bins, right, from 1 to n. And so I can say that this is just the multiplication of all of those probabilities. So 1 minus I-1 divided by, and actually I can start my multiplication from 2 because the first element is going to be in a new bin anyway. So now I want to bound this expression. So one thing that you would probably remember from basic calculus, I hope you remember, is that we always have 1 minus x is less than or equal to e to the power of minus x. Okay. And here I have a multiplication. So I like to have expressions that look like this, because then the multiplication basically becomes a summation. So I can say that this is less than or equal to I from 2 to n. This is my 1 minus x. So instead of that, I want to have e to the power of minus x. So I just say e to the power of minus I minus 1 divided by n. Okay. And, okay, I made some mistakes. So we were supposed to have m balls. So this has to go to m. And this one is also m. This one is also m. This one is also m. But this one is really n, because this is the number of bits. Okay. Now, this is basically e to the power of some of these expressions here. The 1 over n is a constant. I can take it out, and then I just have the sum of I minus 1s there. So this is e to the power of, and I goes from 2 to m. So this would be minus m minus 1 divided by 2m. Okay. So now I know that the probability is this. So the probability that all of my elements are in distinct bins, all of my balls are in distinct bins, is at most this much. But now I have to choose a value for m based on the value of n. Right? And what do I want to do? I want to say that this probability is small. Right? I want to say that with high probability, I have 2 balls that are in the same bin. So how would you choose m to make this probability small? Let's say I want to make this probability into a constant. What value would you choose for m based on n so that this probability becomes a constant? Yeah. So you can, if you set m to be square root of, well, 2n, I mean, a little bit, with a little bit of wiggle room, then we can do something so that this part becomes 2n almost, and this is also 2n. So that works out. So let me see. Yeah, actually, it's good to set m to be the square root of 2n plus 1. And okay, let me see. Should I take the floor or the ceiling? Let's take the ceiling of this. Okay, and if I do this, then this would just become 1 over e. Right? So if m is around the square root of 2n, then the probability that all of my elements, all of my balls go into distinct bins is going to be at most 1 over e. Okay? But this is not what I wanted, right? So what I wanted was to say that the probability tends to 0, because I wanted to say that with high probability, I want to have at least 1 bin that contains more than 1 ball. Okay, but we can again think about the technique that we had on the lecture about complexity classes, where we had an algorithm that worked with some probability, and we would just repeat that algorithm. Okay, so here, every time that I throw square root of 2n plus 1 balls into n bins, there is this much probability that all of them land in different bins. So I have a 1 minus 1 over e probability of success, because my success is the case where 2 balls are in the same bin. Now, but I can just repeat this, right? I can maybe do it 10 times. So if I set m to be 10 times its current value, then this probability is raised to the power of 10, and so on. But now I want it to tend to 0, right? So the number of repetitions should also be a function of n. But I can take a very slowly growing function of n, right? So let's say I take the number of repetitions to be, I don't know, let's say this thing times log of n, or times log star of n. Any function of n that really grows slowly, but tends to infinity. So let's say I repeat this log star of n times. So then this probability would become at most 1 over e to the power of log star of n. And this tends to 0 if I tend n to 0. So yeah, basically, if the number of balls that you have is the square root of number of bins times some function that is not O of 1, that grows faster than a constant, then you have the results that you wanted. Then with high probability, you will have 2 balls in the same bin. Okay. But now I want to show you some other things from okay. So let me show you 2 classical inequalities that we use for finding bounds like this. So we generally want to bound the probability of something happening. And usually it's like the probability of success of our algorithm or the probability of failure of our algorithm. And we want to show that our algorithm succeeds with high probability and fails with low probability. So let me erase this for a second and talk about like probably the simplest inequality in all of probability theory. So let's say that I have let's say I have a random variable x. So x is let's say it's non-negative. And let's say that it always gets real values. So it's a non-negative, real valued random variable. And let's say that I want to find the probability that x has a value larger than some threshold t. Okay. So I can say that this probability is at most the expected value of x divided by t. Okay, and this is called Markov's inequality. Why does this hold? It's pretty obvious, right? Just use the definition of expected value. If the probability that the value of x is greater than or equal to t was more than this amount, then the expected value had to be greater than itself, right? So I can just say that the expected value of x is what? It was the sum over all values that this x could take of x times the probability that my random variable gets that value, right? But now I can consider 2 different cases. I can consider the cases where this value is greater than or equal to t and the cases that it's less than t. So I can just say that this is the sum of all values that my variable can get and are larger than t of x times this probability plus the same sum for values that are less than t. Okay. But now I can easily bound this. I can say that, well, here, all of these x's are greater than t. So instead of all of these x's, let's just put t. So the expected value of x is going to be, less than or equal to, if I just put t instead of everything here, right? And then that would be the probability that x is greater than or equal to t times t. And instead of this one, I'm just going to put 0 because x was non-negative. So its value was always greater than or equal to 0. So yeah. Oh, sorry. I'm always bad with this. The expected value of x, because I'm decreasing this thing. Yeah. Okay. So this proves that the probability that x is greater than or equal to t is at most the expected value of x divided by t. But now I want to see what happens if I give some nice values to t. So what happens, for example, if I say that t is itself some constant times the expected value. So here's one corollary. Let's say that t is just some constant k times the expected value of x. Then we get this. We get the probability that x is greater than or equal to t. So x is greater than or equal to k times its average is at most, well, its average divided by k times the average. So these two cancel out, and this is 1 over k. Okay, so for any non-negative real valued random variable, I can say that the probability that my random variable gets a value that is more than k times its average is at most 1 over k. Okay. But this is not that great, because let's go back to our analogy of balls and beans. What does this tell us? So in the case where we had the same number of balls and bins, we had n balls and n bins, on average, each bin would get only 1 ball, right? So in the best case scenario, I can just use this for constants. So I can maybe bound the probability that a bin gets like more than 10 balls. But that's not exactly what I want. So can we make this even stronger? Can we get a better bound than Markov's inequality? And of course, the answer is yes. And that would be the Chebyshev's inequality. Now, before I tell you about Chebyshev's inequality, I have to probably define what variance is. I mean, I expect you to know this, but in any case, I just give you the definition. So the variance of some random variable x is just the expected value of the difference between x and its average squared. Okay. So again, this is like basic probability. We want to see like, let's say these are the range of values that x could take. And let's say that this was the average value. The intuition is that I want to see how far does x land usually from its average, right? But I want both values, both the case where x is smaller than the average and the case where x is larger than the average to give me some positive distance, let's say. So I just square it so that this thing inside is always positive. Anyway, so the variance of x is the expected value of the difference between x and its expected value or its average squared. And of course, you've seen that some people show this with sigma squared, where sigma is the standard deviation, which is just the square root of the variance. But I don't really care about standard deviation. I work mostly with the variance. Okay. So let's say that I have an x just like before. I want to see what is the probability that x gets away from its expected value, gets away from its average by at least t. Okay. So what is this probability? And Chebyshev's inequality says that this probability is at most the variance of x divided by t squared. Now, how do we prove this? Well, actually, the proof is surprisingly easy, and it's using Markov. So let me just define a new variable. Let's say, just to make my notation easy, let's say whenever I write mu, I mean the expected value of x. So mu is just the average of x. Okay, so I just define a new random variable. I call it y. And what is y? Y is x minus mu squared. So you see that I'm really trying to simulate what we have in the definition of variance. Okay? And so now I want to apply Markov's inequality to this new variable y instead of applying it to x. Okay? But let's start from here. So we have the probability that x minus mu, the absolute value of x minus mu, is more than t. Okay. So if x minus mu is greater than or equal to t, then what does this tell me about y? It tells me that y is greater than k squared. So this is the probability that y is greater than or equal to t squared. Okay. Now what do I want to do? I want to apply Markov. So the probability that y is greater than or equal to t squared is at most the expected value of y divided by t squared. So this is at most the expected value of y divided by t squared. What is the expected value of y? Well, I defined y in this way so that the expected value of y becomes the variance of x by definition. So this is just the variance of x divided by t squared. And this is how we prove Chebyshev. Oh, and by the way, so in Markov, we had this requirement that the variable should be non-negative and real valued, right? So is our variable y always non-negative? Yes, because it's just something raised to the power of 2. So of course it's non-negative. So here I can say that this holds for any x that is a real valued random variable. Right, so here I don't need x to be non-negative. Because in any case, y is non-negative, and as long as y is non-negative, I can apply Markov. Okay. So let's see some examples of how we can apply, let's say, Markov and Chebyshev. I want to find the simplest example here. So let's say that I just flip n coins. So I have n coins, and each one of them I just flip to get a heads or tails. Okay, heads, tails, and so on. So this is coin 1, coin 2, coin 3, coin 4, all the way to coin n. And let's say that each coin comes up heads and with probability half and tails with probability half. Okay, and let's say that, okay, let's say my variable x is the number of heads, number of coins that come up heads. Now I want to, okay, first of all, what is the expected value? The expected value of x is just half of the number of coins, right? But let's say I want to find a bound on the probability that x is at least 0.8 times n. Okay, so if I just flip n coins, what is the probability that more than 80% of my coins come up heads? Okay, now let's apply Markov. So if I apply Markov, this thing is my t, 0.8 times n is my t. And so this probability is less than or equal to the expected value of x divided by t, which was 0.8 n. And as we talked about this before, expected value of x is 0.5. So 0.5 n divided by 0.8 n, and the n's cancel out. What is this? This is 0.625, right? Okay. So this is what Markov's inequality can give us. It can tell us that if we throw n coins, then the probability that more than 80% of them become heads is at most 0.6. But this is a terrible bound, right? Because we expect that this probability actually tends to 0 as n grows. We expect this thing to happen with very low probability. So again, intuitively, if I'm flipping a lot of coins, it would be very weird if the result is that more than 80% of the time I got heads, right? So let's see what Chebyshev can give us. So if I want to apply Chebyshev, I want the probability that x is more than 0.8 n. But I have to write it in this format. I have to write it like as the probability that x differs from its mean by some amount. Okay, so I can say this thing is at most the probability that x minus 0.5 n, which was its mean, is greater than or equal to 0.3 n. You can probably do even better than this, but yeah, if I know this, then if I know this, then I know this. So the probability of this one is less than or equal to the probability of that. Okay. But now I can apply Chebyshev. And what does Chebyshev say? It says that this probability is at most the variance of x divided by t squared. So this is at most the variance of x divided by 0.3 n squared. What is the variance of x? Yes. So the variance of x is n over 4. Actually, it's nice to see how that comes, but for a second, just agree with me that the variance of x is n over 4, and then I'll come back and prove it. Okay, so if the variance of x is n over 4, this is at most n over 4 over 0.3 n squared. Now, not caring about the constants, this one is linear, this one is quadratic, right? And actually, if you find the constants, let me see. Yeah, so this would be like less than or equal to 2.78 divided by n. So some constant divided by n. Okay, so as you see, Chebyshev really gives us a much better bound than Markov. Markov could just give us a bound that was completely independent of n. That's the crazy part. Like Markov's bound was just 0.625, no matter what n is. But what Chebyshev gives us is a bound like this. And if you take the limit of this value as n tends to infinity, the limit of this value would be 0. So using Chebyshev's inequality, I could prove that if I flip n coins, then with low probability, I will have more than 80% coming heads, which is what our intuition says as well. Okay. Now, I really like to do the proof of this variance, but I don't know if we will have enough time. So, as I said, just agree that the variance is n over 4. But if we had time at the end of the session, I will come back and prove it. Let me ask a different question now. Oh, and by the way, Chebyshev is, of course, usually better than Markov, gives us better bounds, but these bounds are not tight. So in later sessions, we will see some other bounds that are going to beat even this one. But at this point, we don't really care because what we wanted to prove was that this happens with low probability, and we got to that. Okay. So let's go back to our balls and bins example, and let me ask a different questions. So how many balls should I throw so that there are no empty bins with high probability? So we're just talking about different variants of this problem. So we were talking like about the probability that I have 2 balls in the same bin, the probability that I have more than k balls in the same bin. But let's say that I just want to cover all of my bins. I want to throw a lot of balls, and I want to guarantee that with high probability, every bin is covered. How many balls would I need to throw? Okay, let me see, which one do I want to erase? Let's erase this one. Okay. So again, I have my n bins. And I'm throwing m balls into them. Now, first of all, do you agree that if I just keep throwing balls and I do it uniformly at random every time, eventually I'm going to cover all of the bins with high probability. Right? So, because if you consider a particular bin, and if you just increase the number of balls that you're throwing, the probability that this bin never gets filled tends to 0. And you can say the same thing about all of the bins. So if I had infinitely many balls, of course, this would fill all of my bins with probability 1. But what if I just want high probability? Okay. So now I want to again look at the same process, but with slightly different random variables. I want to say, look at how many balls I have to throw until I have at least one filled bin. Well, that's trivial. The first ball that I throw fills one of the bins. But then assuming that one of the bins is filled, how many more balls should I throw until a second bin is filled? And assuming that at some point I have I-1 bins that contain balls in them, how many more balls should I throw until I get the ith bin? So this is what I'm going to define. So now I'm going to define again my random variable xi as the number of balls thrown to fill, let's say, the ith bin, assuming that I-1 bins were filled before. Okay, or after I-1 bins were already full. Okay, and when I say ith bin, I don't mean bin number I mean the ith bin that gets some ball into it. Okay. So what do we know about this random variable? For example, what is the probability that xi is 1? So I have thrown a bunch of balls and I have already filled I-1 of my bins, and I now have one more ball. What is the probability that this one ball that I throw fills a new bin? Well, this is quite easy, right? It's just 1 minus I-1 over n. Right? Because I-1 of my bins are already full, and I have to choose one of the empty bins, and I have to throw it there. Okay? Or, yeah. Okay, actually in my notes, I defined these differently, but okay. Or let me just write it like this. It's n minus I plus 1 divided by n. And let's call this thing P because I don't want to keep writing it again. So let's say whenever I write P, I mean this. Okay, what is the probability that it takes 2 new balls? So this means that the first ball that I throw has to go to the I-1 bins that were already full. And then the second ball has to go to a new bin. Okay, so this would just be 1 minus P for the first ball to go into one of the ones that were already full times P for the second. Now, what is the probability that I have 3 balls? Again, the same argument goes on. My first 2 balls have to go into the I-1 bins that were already full. So that's 1 minus P squared. And then my last ball has to go into a new bin times P. So in general, what is the probability that xi is some value k? Well, it's just 1 minus P to the power of k minus 1 times P. And this is what we call, I think, a geometric random variable. So these are the probabilities that we have. And again, what I want you to accept from me is that if these are, if this is the way that this random variable behaves, then the expected value of xi is just 1 over P. And the variance of xi is 1 minus P divided by P squared. So because this is such a common random variable, people just know these formulas. But again, if we have time at the end, I will come back and prove this. But it's kind of unlikely. Otherwise, I'll put a link to the proof on Canvas. So this is the expected value that we have, and this is the variance that we have. But what did I want to solve? I didn't want to apply Markov or Chebyshev's inequalities to xi, right? So xi is just the number of balls between the time that I-1 bins were filled and the time that I bins were filled. So what I want is the total number of balls until all of my bins are filled. So I want the sum of xi's. So let's say that x is the sum of all the xi's. And I goes from where to where? So I goes from 1 to n. Right. Okay. So that's what I want. But now if I want to apply Markov or Chebyshev, I need to know the expected value of x, and I also need to know the variance of x. So fortunately for expected value, we have linearity of expectation. So the expected value of x is just the sum of the expected value of the xi's. I from 1 to n. Actually, I prefer to write this from 2 to n because x1 is kind of trivial, right? x1 is always 1. So x1 is just the number of balls it takes to fill the first bin, and that's always 1. So let's say that I define my x as the sum of xi's from 2 to n, and then I can add just 1 to it. I don't care about that one ball. Okay. So the expected value of x is just the sum of these, but what can I say about the variance of x? So what I want you to see here is that the xi's are independent, right? So it's basically in the definition. If I already have I minus 1 of these bins filled, I don't really care how they were filled, right? So the number of balls that I have to throw to fill the I bin is completely independent of what I've done before. So since these are independent random variables, the variance of their sum is also the sum of their variance. So this is just the sum of the variance of the xi's. Again, I from 2 to n. Okay. Now, based on this, let's see what we can get from Markov, and let's see what we can get from Chebyshev. Okay. What is this expected value anyway? So what is the expected value of xi? It was 1 over p, and p was this. So this expected value is just the sum of I from 2 to n of 1 over that thing, which is n over n minus I plus 1. Right? I can take out the n. So this is n times the sum of 1 over n minus I plus 1, where I goes from 2 to n. Okay, if I put 2 here, I get n minus 1. And if I put n here, I get 1. So I can rewrite that sum. I can say this is the sum of j from 1 to, okay, say n, 1 over j. Right? And so we've seen this sum before, this sum here. We know that it's the natural log of n. So this is at most n times the natural log of n plus, well, we have some less important things. So let's say plus something that is O of n. Right, for the constants that I might have in this sum. Okay. This one. I want. Okay. So that's my expected value. I know that my expected value is n times the natural log of n plus something, and this is small o, so plus something that is small o of n. Or no, actually that's big O, okay, plus big O of n. Now, what can I get from Markov? So I know that my average is almost n log n times natural log of n. So it's natural to ask, like, what is the probability that this x is more than twice that? So more than 2n ln of n. Okay, so what is this probability? This is just going to be less than or equal to the expected value of x divided by this value, 2n ln of n, which is n ln of n plus something that was linear in n divided by 2n ln of n. And this is like 1/2 plus small o of 1. Right? Because this one divided by this one is just a half, and this one is linear, this one is super linear. So if I divide them, this would be small o of 1. And by small o of 1, I just mean a term that tends to 0 as n tends to infinity. Okay. So basically, ignoring this really small term here that we don't really care about, what does Markov tell us? It tells us that the probability that we need more than 2n ln of n balls to cover all of our bins is at most a half. But again, this is not a good probability. We want to show that we want to find the probability that tends to 0. So let's see what Chebyshev tells us. So for Chebyshev, I have to again compute this variance. And let me erase everything that I don't need. So I just need the variance of the xi's. Don't need these ones. Okay. I know that the variance of x is just the sum of the variance of the xi's. So this is just the sum of this, and I'm going to just write it from here. 1 minus n minus I divided by n over n minus I divided by n squared. Okay, so this is our variance. Now, let's simplify this thing. If we simplify it, we will get n times sum of I from 0 to n minus 1 of I divided by n minus I squared. Okay, just do the algebra here on your own. I've done it once, and hopefully I've done it correctly. Okay, so now what I can say is that I have n times this thing, but all of these i's are at most n, right? So I can say that this is at most n squared times sum from 0 to n minus 1 of 1 over n minus I squared. Okay, and I just want to say that this n minus I is j, so this would be at most n squared times sum of 1 over j squared, where j goes from 1 to n. Now, again, this is the part where you should remember some things from calculus and like series and so on. What is the sum of these series if we sum it all the way to infinity instead of just to n? So what is the sum of j from 1 to infinity of 1 over j squared? Yes, it's pi squared divided by 6. So this is at most n squared times some constant, and that constant is pi squared divided by 6. Again, the important point here is that you should know that this sum is just a constant. Even if you don't remember the constant itself, it's fine. Okay, so let's apply Chebyshev. So what is the same probability? What is the probability that the number of balls that I need to cover all of my bins is more than 2n log n? Well, again, I have to write it in the format of Chebyshev. So I have to say this is at most the probability that x minus its average, right? So x minus n ln of n is greater than or equal to, again, n ln of n. Maybe I have like plus O of n or minus O of n. Okay. And so this is at most the variance of x divided by this thing squared. So n squared log of n squared times 1 minus small o of 1. Again, that's just like this nasty thing just comes with us everywhere, but it becomes a small o of 1, so we don't care about that. And the variance of x was n squared times some constant. So we just put it there. So it would just be n squared times this constant divided by this. And yeah, the final result is p squared divided by 6 ln squared of n times 1 minus O of 1. But again, we don't really care about the exact result. What we care about is that this result is basically O of 1 over log squared of n. Okay. So again, you don't need to do all the algebra. All you need to show is this one. Because as soon as we know that, this probability is in the O of 1 over log squared of n, we know that our event here happens with low probability, because this, as n tends to infinity, this tends to 0. Okay? So putting all of these things together, what do we understand? We understand that if I set the number of balls to be more than 2 times n times the natural log of n, then with very high probability, I will cover all of my bins if I just throw these balls randomly. And that's what we wanted to prove here. And we actually found a bound on the probability using Chebyshev, and we showed that this bound tends to 0.